Multivariable calculus, we're in 14.4, day 1. You can see our learning target at the top. I can write equations of tangent planes. And this is very much related and reminiscent at that of what you did in Calc AB or Calc BC. Writing the equation of a tangent line. Well, it was pretty much writing the equation of a line where you would have your slope of that line as the first derivative. That would be your tangent line slope. And of course, you'd be plugging in an x naught, y naught. You did that countless times. And of course, we could use that tangent line to approximate function values close to the given point. Today, we're going to do something very similar. Let's say that we have a surface, and you can see that depicted in this little diagram right here. And you might remember that when we're taking derivatives in this class, we will be taking partial derivatives. You can take a derivative with respect to x, with respect to y. You could wind up with two different curves consequently intersecting vertical planes where x was a constant, like x equals x naught or y equals y naught. And those two curves are depicted here too. Of course, you'd wind up with two distinct tangent line slopes, T1 and T2. And that's really what our partial derivatives were. Well, guys, take a look at this right here. This is really wonderful. In yellow, you can see the equation of your plane. Just as you had in single variable calculus, derivatives are going to show up. You've got this derivative with respect to x, partial derivative with respect to x at a given point multiplied by x minus x naught. Here's a derivative with respect to y, plugging that in times y minus y naught. But look at the left-hand side, z minus z naught. I think you can see incredible similarities to what we started with at the top right part of the screen. Obviously, it's more complicated, but this is, in fact, how you can write the equation of a tangent plane. So let's jump right in and see what we've got. Obviously, we have an x naught, y naught, z naught right here. Let's go ahead and take our derivative with respect to x. You know, this would be our f. I think it would only take a moment for you to see that we would get 4x. And in fact, if you were to plug in the point 1, 1, 3, I think you can quickly see that your derivative with respect to x at that point would be a 4. Likewise, if we took our derivative with respect to y, we would get 2y, as you're looking right here. Once again, plug in your 1, 1, 3, and you can quickly see actually you would get a 2. Well, following this guideline that we'd have z minus z naught equals f sub x at a given point, of course, right here, it's only going to take you a moment to write this equation of your tangent plane. And we'll be done pretty much in a heartbeat. Z naught is 3. Your derivative with respect to x here is just a 4. X naught, of course, is just this 1. Your derivative with respect to y, you can see right here, is going to be a 2. And we'll have y minus, well, our y1 is that. Guys, unbelievably, you are done. That's it. That's your equation of your tangent line plane. But of course, if we were to use that, let's just say that we have this tangent line plane. Very clearly, this is not your surface. This is not the actual function that we are working with. It's, you know, a plane that you could see depicted up here. You could have like this darkened in surface, but you can envision a plane just touching, just being tangent to that point right there. You know, as we move away from the point in question, as we let x equal 1.1 and y equal 0.95, what's the benefit of this? Well, we can very, very quickly get estimates for the function at hand. and it's not that difficult to do that. And as we work through this is going to be a 4 times a 0.1, and this is going to be a 2 times a negative 0.05, and here you have your z minus 3. So 4 times 0.1, you get a 0.4. 2 times negative 0.5, well, that's going to be a negative 0.1. So this just becomes a 0.3, right? And then when we are adding a 3, we'd get z equals 3 plus 0.3. So this is not your real function value at this x of 1.1 and y equals 0.95. It's not what your z value truly equals, but it's an approximation. It's a very nice estimate. Let's go to page 2. In a shocking twist, and this can be very strange, but it can happen. It's possible for a partial derivative to exist where the partial derivative is not continuous. It's pretty strange, but it can happen. Page 941 provides such an example. Kind of an extreme. How do we deal with this? Well, very, very, very importantly, when you take your partial derivatives, if you know that those partial derivatives are continuous at that point, then your function is said to be differentiable. The question about whether a function is differentiable, that is, whether you can take a derivative or not, is super, super important. Of course, continuity is required. So we're always going to take our derivatives, but quickly also determine continuity. So let's take a look at this next example. We have a function x e to the xy. Show that this function is differentiable at the point 1, 0. Find its linearization, find its tangent plane equation, and then use that linearization to make an approximation. Well, it only takes a moment to take a derivative with respect to x. We will need the product rule to do that. We'll have our first function multiplying by the derivative of the second, the derivative of e to the xy with respect to with x. Well, we're going to have an e to the xy, but the derivative of that xy is just going to be a y. And then what? We'll take our derivative of u, which is just a 1, and here's e to the xy. Guys, you can very quickly see that your function is continuous at the point 1, 0. And you can see you don't break any rules of arithmetic when you do that. More to the point, if we were to plug in 1, 0, you could quickly see this first component disappears to 0 because y is 0. And then it's e to the 1 times 0, that's e to the 0, which is 1. You can quickly see this is just a 1. When we take our derivative with respect to y, it's a little bit easier. We don't need a product rule. E to the xy, well, you'll get an e to the xy here, but taking your derivative of that power with respect to y is going to have an x come out. X times x is x squared. And once again, this is going to be continuous at the point 1, 0. And if we plugged in 1, 0, I think you could see very quickly once again, you would get just a 1. So here's really what we need to do. We have the point 1, 0, but you know what? We need to find z naught. If I did that, if I plugged in a 1 and a 0 into the very first part, I think you can quickly see that you'd get a 1. Right? Because we'd have 1 times e to the 1 times 0. And why is that so important? Well, the linearization is going to look exactly like this. And it's only going to take us a moment to clean this up. So this is z minus 1. F of x is going to be a 1. This is x minus 1. This is going to be a 1 right here, but we'll have y minus 0. And, wonderfully, this could be your linearization. This could be your tangent line equation. But then we want to approximate for b f of 1.1 and negative 0.1. Well, we'd have z minus 1. Here's a 1, and we'd have 1.1 minus a 1 plus 1 times, well, this is negative 0.1 minus a 0. 1.1 minus 1, that's a 0.1. 0.1 times 1 is 0.1. This is just going to be a negative 0.1. So we'd have z minus 1 equals 0. Z equals 1. This is not your real function value. It's just a good estimate. All right, as we wrap up here, tabular problem. Wow, tabular problems get to be so very, very common, even in multi. That's calc reform. The heat index, it's the feels like temperature. It's a function depending on the actual temperature. That's what we're going to call x. We're going to have that right over here. And, it looks like x naught's going to be 96. And the relative humidity, 70% right there. So, what we have very quickly is a 96 for our x. For our y, we've got 70. And, of course, you can see right here, that would be a feels like temperature of 125. So we just have this information with the table, nothing else. We're not given an equation. And we're trying to estimate the heat index when T is equal to 97 degrees Fahrenheit. You're going to see that's not on the table. And when the humidity is 72, you're going to say, wait a minute, that's not on the table either. So, of course, what we're going to do is get this estimate with the tangent line plane. We're going to say, look, we need to go ahead and write this out. We happen to know what our x naught, y naught, and z naught are, but you can think, my goodness, how do I find f sub x? Well, I'm doing this fast. F sub x means y is constant. Y is constant, and your y value starts at 70. So tell you what, we can go ahead, and I'm just going to momentarily highlight this and say, look, if y is equal to 70, it's fixed. We just have this right here. And we're going to do this in a tabular format. We're going to say, look, of course we have 96 and it feels like temperature 125. I'm going to actually go one step below here. By the way, just like you did last year in single variable calc, you could have gone with the 94 degrees also. But what I'm going to do is go take a y2 minus y1 all over x2 minus x1. And you can see where we're going with this. 133 minus 195 is an 8. That's 8 over 2. That's a 4. Likewise, when we take a look at f sub y, we're going to say x is constant. And if x is constant, that means x equals 96. Well, this time, tell you what, I'm going to go ahead and just focus in on x being 96. And when we do that, of course, now you're going to be looking at some different variables, different ordered pairs. And we could very quickly say, well, how about right now we go 70 and 75? We could say the 70 matches up with the feels like temperature of 125. And then we could go up to 75 and have a feels like of 130.